Hello and welcome. Fluid Dynamics Part 2. Alright, so now let's look at the dynamic part of fluids. So we're going to be dealing with ideal fluids, and these are the conditions for the ideal fluid. Non-viscous, no frictional forces between parallel layers. So two layers of fluids, no friction in between them. Great. Incompressible, homogeneous density, same density throughout the entire fluid. Okay, non-turbulent, velocity and pressure stays the same throughout each phase of motion. Okay, what this means is if the pressure and velocity stays the same throughout each phase of motion, then the change of mass from each phase will stay the same. Okay, so here we see at the bottom here, delta M is equal to delta M, basically saying that rho times the area times the velocity 1 will be equal to rho times area times velocity 2. Does that mean that necessarily that area will equal area over here? No, it does not. Velocity equals velocity here? No, it does not. Most of the time, density equals density, though. But so usually this formula can reduce down to just area velocity times area velocity, and we'll see that a little bit later. Actually, we'll see that right now in this formula, or in this problem right here. If area times volume is equal to 7 meters cubed per second, cubic meters per second, 7 cubic meters per second, because the area was 1 square meter and the velocity was 7 meters per second on one side of a diverging pipe, then the area reduced by half. What happens to the subsequent velocity? Well, great, I'm glad you asked. Maybe that can satisfy as being half. Okay, that kind of looks like half. All right, half its original shape. All right, so if this is area 1, area 1, which is equal to 1 square meter, and the velocity through here is 7 meters per second, and this is now area 2 is equal to 1/2 meters squared. Okay, then what is the velocity coming out? Okay, let's take a look here. So it's the same fluid throughout. So we have rho 1 A1 V1 is equal to rho 2 A2 V2. Okay, just like the formula said, rho stays the same. Okay, so now we have A1 V1 is equal to A2 V2. Area is on the left here 1 meter squared times 7 meters per second. Oops. Is equal to 1/2 meters squared times V2. Okay, how do we get V2 by itself? Well, we'll divide both sides by 1/2 M2. Whoops, keep writing that as squared. It is not squared. That is, oh, meter squared. It is meter squared. Sorry about that. I am just up too late tonight. 2, 2, 2. Okay, great. So now, both sides. Okay, great. So this is actually turns into 2 times 7, 14 meters per second is equal to V2. Okay, let's try it out. So double check the math, I guess, huh? So 1 times 7, we're saying, is equal to 1/2 times 15 divided by 2 is 7. Great. All right. So that checks out. Good deal. No. So let's get back to this. Ideal fluid. All right, that is the ideal fluid conditions. Bernoullis equation. So how to get Bernoullis equation? First of all, let's start with the basic conservation of energy equation. Work plus, and I put work in parentheses because you may not have seen it with work, but work is there, okay? Work is there. Sometimes it's in the equations, sometimes it's not, okay? In your particular physics class, you may not have used it, or you may have, but in this case, it is there for deriving this Bernoulli equation. So work plus potential energy plus kinetic energy, it's translational kinetic energy, on the initial side is equal to work and potential plus kinetic final, okay? Divide all of it by volume, and you get this. Well, how do you get that? How does work turn into pressure when you divide it by volume? Well, work is equal to force times distance. Do you agree? Yes. Okay, we all agree. Force times distance divided by volume, okay, is the same thing as saying newtons for force, meters for distance divided by meters squared cubed. That's a 3 right there. Dang it. And when you cancel these out, if that's a 3, which is what it's supposed to be, can't believe that happened, this is what it looks like. Force times distance divided by volume in terms of units is newtons times meters divided by cubic meters, okay? Turns into newtons per square meter, which is force per unit area, which is pressure, okay? Great. So now, and mass divided by volume is equal to rho, okay? Great. So yeah, so when we divide mass in each case here by volume, we get rho, okay, which is where it replaces right here, 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 and here, okay? The bottom of a rain barrel is held at 5 feet above the ground, okay? What is the velocity of the water coming out of the pipe from the bottom at ground level, saying that the bottom is at ground level, okay? Well, first we'll start out with this new equation we just learned, okay? Density and pressure stay the same, okay? So if density stays the same and pressure stays the same. So first of all, if pressure stays the same, we're going to do what's called combine like terms, and we'll subtract pressure from both sides. If this is 1 Pascal and that is 1 Pascal, when we subtract them, what do you get from 1 minus 1? 0. So it's not there anymore. Great. So if that's gone, and we divide everything by rho, and if that is 1 kilogram per cubic meter, this is 1 kilogram per cubic meter, so on and so forth. You divide it out, and it just turns into 1. Okay, those are all 1s right next to it. Okay, they do not turn into 0. They turn into 1. Okay, great. Velocity of the water in the barrel is 0. So if you're talking about the water inside the barrel, talking about the water inside this barrel here, that velocity, 0. Okay? Standing up a particular distance. I don't know, you say 5 feet or something? I don't know what we used. 5 feet, oh, that's horrible. Should be meters. Anyway, I don't solve it out anyways. 5 feet, sure. And a small spout comes out here and releases water. water comes out here. Okay, great. And at what velocity does it come out? Okay, so now let's see what happens. Velocity in the barrel is 0. So, I don't know how I turned to red. G times H, because velocity in the barrel was 0. This is 0 right here, so it no longer exists over here. Height of the water coming out of the barrel is 0 because of our original statement at ground level. So this turns into 0, so it is no longer here. Now set the equation equal to final velocity. So we had a 1/2 here. We multiplied 2 to both sides. When we multiplied 2 over here, we got 2GH. And this was squared. What is the opposite of squaring? Taking the square root. Great. And that's the way it works. Okay. Fluid through a pipe with a changing cross-sectional area. Now this is a little bit difficult. Please follow along. What is the velocity of water coming out of the bottom of a pipe with an entrance area of A1 and an exit area of A2, such that A2 is equal to A1 divided by 2, half of the original cross-sectional area, and a height of H equals 0 at the second position. Okay, pressure is constant. All right, so now let's figure this out. So we have this original Bernoullis equation right here, but no velocity. Okay, we don't have a value for any velocity. So we start with this equation that we found at the beginning of this whole entire talk. Okay, water in and water out. What does that mean? That means the same density on both sides here. Okay, that plays into another part of this a little bit later, but for now, area times velocity is equal to area times velocity. Okay, so now water in and water out. So that means that A1 V1 is equal to A2 V2, and we put everything in terms of velocity too, because we want to know what the velocity of the water is coming out. Okay, so we want to replace what V1 is. So we take this and we put it in everywhere you see a V1. Okay, so here we go back to this equation, and we first of all say that pressure is constant. We get rid of the pressure just like we did earlier. 1 Pascal here, 1 Pascal here, or whatever it is, we just subtract them and they go away. Okay, water in, water out, that means all the densities go away. Okay, that's just for this case. I don't know that it always happens that way. I'm just doing this example in that manner. Okay, but now, as you see where we had a V initial over here, which was V1, we replaced it because V1 is now equal to this mess right here. Okay, we put all this in for V1 and take a look at this. We square everything in there. All right, V2 is still V2. All right, so pause it if you have to pause it, but this is now what V1 is. Oops. This is now what V1 is in terms of V2. All right, so moving on, height is 0 at the bottom. Okay, that means that the height component goes away. It's 0, okay? 0 times G is just 0. All right, so now we have this GH plus 1/2 of this V1, which this represents V1 squared, is equal to 1/2 V2 squared. We multiply 2 to everything. Multiply this by 2, multiply this by 2, and multiply this by 2, and we get this. Okay? There's no more 1/2s. All right? Additionally, you see this happening. What we did was we subtracted this from both sides. Okay? It ended up over here. Okay? First of all, let's write out what actually happened here. It's getting kind of convoluted, I can tell. So we say that GH plus 1/2 V2 squared A2 squared divided by A1 squared is equal to 1/2 V2 squared. Okay? First of all, we multiplied everything by 2. 2, 2, 2. Left with 2GH plus V2 squared A2 squared divided by A1 squared equals V2 squared. Okay? 1/2 cancel with the 2, 1/2 cancel with the 2. Okay? Great. Then we subtract this from both sides. Okay? Both sides. So 2GH is equal to V2 squared minus V2 squared times A2 squared over A1 squared. All right? Now we're going to factor out the V2. 2GH is equal to V2 squared 1 minus A2 squared over A1 squared. Now this is a big important move right here because this is one of the more important aspects of math is factoring things out so that you can just get one of these terms. Okay, get that one term so that we can divide this mess, divide both sides by this mess right here. Okay, and I'll show you what that looks like here in a second. Okay, take a look here. We divided, this is where we're at on the other page. We just divided this, divided both sides by this. Okay, and we got this. All right, we divided both sides by this right here, and we got this. Okay, great. Moving on, previous equation in its entirety. So you can write that down if you'd like. But you should try to do this with a changing pressure. See what it looks like. It's a little bit, it's a couple more terms in here, but it's not impossible. Okay? All right, great. So here's a problem. Blood pressure difference. If the density of blood is rho and the distance between the heart and the toes is h sub heart, ignore the actual flow of blood. We're going to make this kind of easy, very basic. Then the difference in blood pressure from the toes to the heart could be written as follows. So we start with this equation because we are ignoring all of velocity. We're saying that velocity is the same in both parts, okay? Which it is not. But the height of the toes is 0, okay? So we got rid of that height component over there. So the difference would be this, rho GH. We subtracted the pressure at the heart from both sides, okay? So now we have this. Now we can put numbers in. If the density of the blood was this, and the height from the toes to the heart was this, then we just put in our numbers to get the difference. 13.4 kilopascals. Okay, that's actually pretty high. It's pretty tall. But that is the blood pressure difference between those two locations. Okay. What does that say about medical stuff? I'm not too sure. But that's the answer. All right. Well, thank you very much, and look forward to future videos. You have a great day.